Right, thanks everyone. So today I'm going to talk about our project GrainDB, which is a hybrid graph relational database management system we're developing with the goal of extending an analytics RDBMS, specifically DuckDB, with graph modeling, querying, and visualization capabilities. And this is joint work with Guodong Jin, who is a PhD student at Renmin University of China and has been visiting my group for the last two years. So let me motivate GrainDB by discussing some appeals of trying to develop a relational core hybrid system. And by that, I mean, extending an RDBMS with graph querying, modeling, and visualization capabilities. So, ever since the birth of our field, there has been a dichotomy between relational systems that support modeling application data as tables and systems whose core data structures are graphs or trees. And the first appeal of a hybrid system is that there is no perfect data model, right? So tables are great at certain things. A lot of legacy data is represented as tables. They're great at representing non-binary relationships between entities, and they're great for normalization. Big chunks of databases end up being essentially data that normalizes the rest of the data to a data replication. So you get, for example, in relational databases, zip codes, days, dates, addresses, and these are things that are not really very natural to think of as anything but tables. They're not really very natural to think of as nodes or edges, for example. At the same time, if you talk to users of graph databases, they'll tell you that one of the appeals of graph databases or graph model is that it's closer to their mental model of how they see the entities and relationships of the application data that they represent. Similarly, there is no perfect query language. SQL is great at certain things, very popular and established and suitable for standard data analytics preparation and ETL text, but it's not the best language to write queries that have recursive components. So again, if you talk to users of graph databases, they'll tell you that they find it easier to write some recursive join queries, for example, in the syntax that graph query languages provide. So for example, they'll support this clean star syntax to represent one or many joins, right? And from a vendor's point of view, if you've got an RDBMS already, but you want to have a product in the graph database management space, then it's cheaper and quicker to build and leverage your RDBMS to support some graph modeling and querying on top instead of developing a complete separate code line. Right. So here's our vision for GrainDB. We want to make and take an analytics RDBMS and make it competent on graph workloads broadly. At the lowest layer, pictorially, we have a relational system, DuckDB in our case. So everything in this layer is relational. But we want to make DuckDB more competent on graph workloads by integrating to the core of the system several techniques. And these are essentially techniques to make it competent on several types of joins. So predefined pointer-based joins, which is the topic of this presentation. Factorization, worst-case optimal joins, which are techniques to make for many-to-many joins, which are prevalent on graph workloads, and some techniques to make it more competent on recursive joins. On top of it, this relational layer, we want to support some way for users to model portions of their database as a graph. So they could say that this person table, I want to also model as a vPerson node, or this nodes table, we want to model it also as an e-nodes edge between vPersons. And given this hybrid model, we want to support GSQL style seamless table graph query. Okay, so GSQL is Tiger Graph's proposal to support seamless table graph querying, where essentially it's SQL compliant, but in the from clause, you could specify some of these joins, presumably the recursive ones, as graph patterns, but seamlessly join them with tables, in this case, the address table, for example. But it's essentially SQL compliant. And at the front end, you want to have Neo4j Bloom style graph visualization, which is another thing that users like a lot. They want to see query results as nodes and edges, which is closer to their mental model. Then also, there's very elegant ways to explore the database interactively, which a lot of relational systems do not support. Okay, so that's our overall vision for where we want to go with GrainDB. And in this talk, I'll talk about our first paper, which described how we integrated pointer-based joins into DuckDB. And I'll talk about that in the remainder of the talk. Right, so a primary difference between graph database management systems and relational systems is that joins in graph database management systems are pointer-based in nature, while they're value-based in joins. So let me just give an overview of joins in graph database management systems. So over here, I'm showing you a financial network graph with accounts and transfers between accounts, and a simple query. It's a two-hop query of A transferred to B, B transferred to C, where the middle node is owned by Alice, and the simple query plan, scanning the middle node, extending backwards to A, one join, extending forwards to C, the second join, right? So the first thing that graph database management system globally do, it's kind of universal to all of them, is that they'll use node IDs, which are effectively pointers. They're used as pointers in these adjacency list indices. And then let me just simulate maybe a simple tuple at a time processor. The scan node operator could scan and find the Alice's record, but put the ID of it, this pointer, effectively into the B variable. And then using this node ID, we do one backward pointer chasing to match the backward edges, and then a second pointer chasing to match the forward edges to produce output. So essentially, this ID-based nested index loop join is the nature of the joins. And now, not that this contrasts with the value-based joins in relational database management systems, because this query effectively contains two equality joins, but there was no value comparison that happened in the execution that I simulated. All right. So as such, it could be faster than value-based joins. So the way we have integrated pointer-based joins into DuckDB is, here I'm showing you the SQL equivalent of the query with two equality joins and the table representation, relational representation of the same data. So I won't go over it, but we have this, I have this RID columns here, which are implicit columns. So they're not materialized, which are the row IDs or record IDs of the rows in each table. So we're going to use those. I'll tell you how in a second. So the first step of benefiting from pointer-based joins is the user comes to DuckDB and predefines a primary key foreign key join. So in this case, the join of accounts and transfers based on owner and from, essentially for each account getting its forward transfers, right? So once this happens, the system does two things. So we're going to use these row IDs that columnar systems already use as system level pointers. And we're going to do two things. First is we're going to take the foreign key table and extend it now with a materialized RIDs that point essentially to the rows in the accounts table that each row joins with. So for example, and then the second thing is we're going to create an index analogous to an adjacency list index of primary key RIDs to the foreign key tables RID. Okay, so for example, Alice's RID in the accounts table is 1, so its RID index is going to contain 1, 4, 5, and this FRID column is going to contain 1s for rows 1, 4, and 5, because those are essentially pointing to Alice's RID, right? And I'll show you how we use this. The second step is that we have rule-based query planning, where we generate a default plan by DuckDB, which uses hash joins for equality joins. And then we're going to do a rule-based transformation of this plan by replacing some of the hash joins with what we call SIP joins. These are modified hash joins, and SIP here stands for side-bay information passing, and scans with scan semijoins. Okay, I'll show you, it'll become more clear, but basically we take this plan. Here are the operators that we replace with our own modified hash join and modified scans. And here's the important part. I'll just simulate what happens in this first join in this plan in the rest of the talk. So let me make space for that. So the way the join will happen instead of a traditional hash join is that the scan account table, the scan account operator will scan Alice's row as before, but it will also attach the RID of Alice, which is 1, and send it to this modified hash join, which will create a hash table as before. So this is the build side. But instead of using the value owner Alice as the key, it will use the RID. So it will use the integer, dense integer, as the key. And the second thing it will do is that using the RID index, it's going to create a semijoin filter. So this mask is essentially identify the rows from the transfer edges that will successfully join. So this semijoin mask will be sent to the scan semijoin through side-bay information passing. So the scan semijoin, instead of scanning all the rows and transfer, only scans the rows that are guaranteed to have a successful join. Okay, so the scan semijoin essentially will use this mask to perform a semijoin during the scan. So we'll use RIDs as pointers. Okay, but the nature of how we use it is different than graph databases. Instead of this nested loop type of joins, we use hash joins essentially, but which ensures that all scans are still sequential instead of generating these non-sequential scans, which some nested loop joins plans generate. This is my last slide, just to show you very, very quickly the type of sort of performance gains we've got by replacing some value-based joins with pointer-based joins. Here I'm showing you LDBC 10 benchmark, a simplified version of it, focusing on the joins. and the box plots for vanilla DuckDB, GraphLowDB, which is a in-memory graph database we are developing in my group that does pointer-based joins only. If you look at the vanilla systems, there's about essentially an order of magnitude difference in the median query runtimes. But once you replace value-based joins with pointer-based joins, we can close this gap in GrainDB and make GrainDB essentially competitive with GraphLowDB, right? So here's the one-man hero who's leading this single-handedly. This is the guy, one of the guys you should be after if you're looking for somebody who's very competent working at the internals of your systems. And the link to our paper, which is under revision right now. It's not yet published, but we have a tech report, and here's the link. Hopefully you can see the published version in a couple months. With that, let me thank you.
Thanks, Semih. Yeah, you are slightly over, but there is room for one question. I would like to compliment you on the selection of DuckDB as your platform, of course. Is there a question? In the meantime, I can tell you that upcoming in DuckDB is an optimization that will actually switch from hash join to positional join in case the join keys on the build side are dense. So maybe that's also interesting for you.
Okay, that's interesting. Okay, that's interesting and very relevant. So the version we're using doesn't have that feature, but that's interesting.
No, it's not yet pushed, but it's close to it.
I have a question.
Nikolai.
Semih, very interesting. So what made you do this actually? Because from the first sight, it's a bit strange, right? So you're using relational backend. I mean, of course, many people did that back in the day, but then somehow decided to write their own backends. So what was the thinking?
I think the more like so we've been working on a lot of techniques in terms of graph databases. I mean, the more I work on it, the more I also am convinced that there are like a lot, basically graph databases are also relational at the center. If you look at sort of the plans that Neo4j generates or GraphLowDB generates, I mean, we are doing relational joins, we are doing scans, we are doing essentially projections, aggregations and whatnot. So I stopped seeing, I mean, I do see several techniques that are adopted by these systems, but at their core, they're all relational. So I stopped seeing something that is fundamentally contradictory when you wanted to optimize the joins or when you want to integrate the types of joins we do in GraphFlow to say a relational system. So I think there's nothing contradictory between them. So I thought this is doable. I think it's just overall a good idea. There's, as I said, there's many appeals of trying to provide and reuse a single RDBMS than trying to develop separate code lines. So this is an attempt to show, unlike, there is several approaches that have tried to build graph databases, but they're purely translational. So they don't change the internals of the system to make it more competent. But if you look at the literature, like worst case optimal joins, factorization, things you're trying to develop on Avant Graph 2 or VR integrating the GraphLowDB, they're all relational techniques developed by POTS community, always explained in relational terms. Now, they're not graph techniques. They just happen to find great application in graph workloads because graph workloads have many joins. So I tried to essentially take a different sort of study how would you integrate these techniques into relational systems, because I think there's a lot to do there. Like the ways Dan Altuani has integrated factorization, I don't think is the right way. It's not very practical, I think. So we're essentially doing research in this space.
Okay, thank you, Semih. Thank you, Semih. We regrettably do have to move to the next speaker.